So let's get started. What did we talk about last time? Normal distribution. And, oh, that's a pretty good one. There we go. What about the normal distribution? Remember? Do you remember? It can be right or left. So I say again? Skewed. It can be skewed right or left. Absolutely right. Absolutely correct. Right. We normally assume it's symmetric, but you can have outliers on one side or outliers on the other side, usual number, right? So Michelle's absolutely right on that. We also talked about how it's represented by a mathematical function. And so, while no one ever actually calculates that by hand, Excel has that built into it. And so you can learn things about it by looking under the area under the curve. You can figure out, for example, portion of people that lie within a particular range. You can figure out under a particular range how far it is to go back. And I mentioned at the end of class that this has some practical applications. And we can see that in warranties. What is a warranty? Exactly, right? So if something breaks or doesn't work, you can get a new one replaced, right? It won't cover it. So with that in mind, why do companies offer warranties? Yeah, Julia.
Or,
Excellent. I love how you phrase that too, because you considered both parts of it, right? So Julia rightly notes that longer warranties are good because people will feel confident in buying the object, right? But shorter warranties are good because if you replace too many things, it's too expensive. And you said in the beginning, they have calculated in such a way that gives us an idea that they know how much they're going to replace. Okay? And so what we're going to do is that calculation, at least a part of it. Because there's going to be some art in this as well, some marketing, right? As you know, for example, not everyone even always catches in on the warranties, but this will give us a starting point as to figure out what should we set a warranty at. So let's imagine that we are working with a company that makes dishwashers. The dishwashers maybe last an average of 10 years.
Oh, wow.
I know, are they really long-lasting dishwashers? No, I'm just working with some numbers. I don't think they last. Do they last? I don't really know how long dishwashers last.
Some companies don't last, they just malfunction. There's so many issues with dishwashers.
Yeah, that's true, because people are putting food in there. It depends on how, yeah, that's true.
How much you use it.
And then all these things. So we're going to do an average. You're right. We're going to say 10 years until, like, on average, until it really breaks down, you have to get a new one. Right? Because some things are beyond repair. And let's say that the standard deviation, if you want to change that to washing machines or dryers or something, that's better. Or whatever you want to put it to, HVAC, whatever. Standard deviation is, we'll say, 1.5 years. And we're trying to figure out what our warranty should be. Let's imagine that the accounting department says we can afford to replace 4% of all dishwashers. 4% of all dishwashers we sell. Okay, we good so far? What should we set the warranty to be? So what we are essentially doing is we are noting that there is a standard deviation. I'm sorry, not a standard deviation. We're noting that there is a normal distribution of performance with 10 here at the middle. We are trying to figure out if we put 4% into this shaded area, what is that value X? Are we good? So everyone follow what we're trying to do? Let me hit the lights then.
You say 4% of top, what's that number?
An X with a question mark?
Oh, okay, yeah.
I'll make it bigger. We don't know what that is. So What do you think we do? How would we fix this problem? Let me make the 10 bigger.
We're looking for the 4%, right?
We are looking for what value of x would give us 4%. Let's first put in these values. I'm going to put portion. I'm going to put in 4% here, or 0.04 if you want to do it that way. Average is 10. Standard deviation is 1.5. And then I'm using normal invert, probability, mean, standard deviation. So the probability is just going to be our portion. There's always going to be bounded between 0 and 1. What's our average? What's our mean? Don't all talk at once. 10. Thank you. And then our standard deviation is, of course, the 1.5. And if you don't like that 10 years because you think it's too short, you can always change it to 5 if you want. You're getting, everything will update. But let's just stick with 10 because that's what I have in my notes. Let's zoom in a little bit more. There we go. So we got 3.74 roughly. I'm sorry, that's 7.374. 7.374. Everyone get that? Yes? Here's the problem. You cannot, on an advertising campaign, put in 7.374 year warranty. Right? What the hell is that? So what should we do? Should we round it up to 7.5 years, 7.5 year warranty? No, why not? Julia? If we round it up, then we're going to replace more than 4%. But if we round down, then when we protect ourselves, we will not hit that 4%. Remember, we can afford to replace 4%. Can't afford to replace more than 4%. And you can check this too if you're curious, because you can just put in norm distribution. We can put in, say, 7.5 as our x with 10 and that and cumulative, and we are actually getting much more than 4%, almost 5%. And now we're in financial trouble. Not a huge financial trouble, but that's not good. So, but if on the other hand we do, let's actually copy and paste this down. Yeah, if we do, we can do like 7. That's a nice clean number, right? I don't know why it's giving it to me in that. I want it in %. Now we're doing 2%. But now we have something to work with, right? What's nice about this number right here is it's a base value that we can work with, that we can reference. And then there's these other complexities like what would be good marketing, and maybe like what % do people actually return? Maybe we can do some research, and maybe maybe it can be we can adjust it accordingly. Any questions? No. So one of the nice things is like someone suggested, hey, what about 88 months? That sounds pretty cool. 88-month warranty. I think it has a nice ring to it as far as like advertising goes. What do you think? 88-month. Could we do an 88-month warranty? Would that be something we could do? How would we figure that out? Yeah, we divide 88 by 12. What did I say again? Exactly. So could we do an 88-month warranty? Yeah, absolutely. It's less than our threshold of 7.37. If you go higher, you're going to naturally encounter closer to the mean. You're going to actually cover more area, and then you're not going to be at that 4%. But if you go lower, then you're fine. So this gives you some base value to work with. Let's do another one. I'm going to do a slightly different version. That I have in the notes for this one, just to make sure that we are all on the same page. Let's do delivery. So let's imagine that you work for a shipping company and you want to offer a guarantee for your shipping. And it's a shipping company, the ships that take months to travel from different places. So let's imagine that on average, because this is business facing, right? You're selling to businesses. So we're not doing like Amazon 2-day thing, but we are saying like maybe it takes an average of 5 months. Maybe ship something, they get a shipment over from China, over from Vietnam or somewhere, with a standard deviation of, we'll say, I don't know, let's just make our numbers simple, 2 months. And we can afford to give refunds to, say, the slowest 7%. Right. I'll give you a refund, or I'll give you a partial refund if it takes longer than this threshold for your stuff to arrive, for your shipment to arrive. How do we do this in Excel? Anyone? Think about what we have here. We have the portion, the average, the standard deviation. So what do we do? Let's just plug it in. So you just want to change everything? Okay. So average is no longer 10. Average is now 5. Standard deviation is no longer 1.5. It's now 2. And we don't have 4%. We now have what? 7. You can get rid of this stuff. This isn't helpful for us right now. So does that make sense? 2 months. Think about what just happened, Laura. You just bankrupted the company. If it takes longer than 2 months, we're going to give you a refund? The average is 5. How is that possibly 7%? What did we do? What mistake did we make? Yeah, Michael?
So the ones on the left are actually the quickest because the smaller the number, the faster it gets there. So the slower ones are actually the bigger value.
Exactly. So note that both when we were talking about dishwashers and we talking about deliveries, in both cases we have to be working with time. But as Michael knows, sometimes things, sometimes low values of time are bad, like dishwashers not lasting very long. But sometimes low values of time are good, like it takes very little time for it to last, for it to be delivered. In this case, low values of time are good, high values are bad. High values are beyond. Like the slowest means they take longer, means that they're higher. So we want to find 7% over on this side. How do we do that? %. That's right. Oops. Guess I just put in 93. Oh, I knew it. I should have put in 0.93. There we go. 93%. Should we round up or down? For one, let's appreciate that this is greater than 5, so we're probably not bankrupting anyone. But should we round up or down? Yeah, Michael?
For the same reason. So if you round off, it's now looking at the ones that are 8 months, and then as opposed to like 7.95. If you're round down, if you're looking at all like faster ones.
Yeah, exactly. Again, we're trying to pull away from the mean, right? We're trying to keep in context of what we can afford to do. And so if we round up, we're getting farther away from the mean. This value becomes smaller, and we won't have to worry about not being able to replace stuff. So we want to get farther away. Here, when we were doing the warranties, we rounded down because lower numbers were better. Lower numbers were worse. Here, we're rounding up because higher numbers were worse. We're trying to shrink that tail. Everyone follow that? So let's move on to confidence intervals. Confidence intervals are a way to get a good idea of what's going on in the population. Remember, when we take a sample, we are getting essentially, the lack of a better word, a guess as to what's going on. If I want to get figure out what the average hair length is, for example, I'm taking a sample of people, but I recognize that that average I find, based on that sample, might be wrong for random reasons. Might be a little bit higher, it might be a little bit lower. And the confidence interval tells us, based on various parameters, how much higher I should estimate hair length to be, how much lower I should estimate hair length to be. It is an interval. It starts with a point estimate. Which is the best, I don't want to say guess, to the true population mean. The interval itself is based on something called a confidence level. I want to make sure I get all my confidence level is the probability the is in the interval. Now, appreciate we're going to have to make an exchange or a trade-off between two different ways of thinking about this. On one hand, we can have a very high confidence interval, and these are always done in percents, like 90%, 95%, 99%. We can have a very high confidence interval, and that means that we have a pretty high likelihood of including the true population mean in this interval. However, the larger the confidence level, all things being equal, the wider the interval. And so on one hand, we're saying, oh, we know what's going to happen. We know generally what's happening. At the same time, we have to get vaguer. So to give you an extreme example, I don't know what percent of the US population needs some sort of corrective lenses, eyeglasses, contacts, whatever. I don't know what percent that is. But I guarantee you it is somewhere between 0 and 100% of people. Sounds about right, right? I've really never, but is that helpful?
No.
No, right? It is not helpful at all. At the same extreme, let's imagine that I take an estimate based on like maybe, I don't know, a couple of people I know, let's say 10 people, and 3 of them need glasses. And so I'm like, okay, 30% of people need glasses. Is it exactly 30%? In all likelihood, probably not. If I say, you know, there's only maybe about a 2% chance that it's 30%. Is that helpful? No. It's slightly more helpful than saying it's like somewhere between 0 and 100. It's more helpful than that. But it's still like only 2% chance of a 0.3, of a portion of 0.3. So confidence intervals give us a middle ground between that. We might say something like, look, there's a 90% chance it's somewhere between 20 and 40%. That's helpful. Or there's a 99.9% chance it's between 10 and 50. On one hand, is that more helpful or less helpful? I increased the confidence level, so we're more likely to be capturing the true population mean. But it's also less helpful because I had to widen the range. So that's the intuition as to what we're doing. And what we're going to be covering today is the math behind it and how we get from this basic idea to there. First, we're going to have to get some terminology down. Here's our friend, the normal distribution. And the last class, we talked about the empirical rule. What was the empirical rule? Not just a normal, standard normal. Yeah, Julia.
About 68%
Uh-huh. Two standard deviations, plus or minus 3, right? Yeah. Exactly. The area that we do not include in that, so you can think of like 99.7% as a confidence interval, confidence level, and 95% as a confidence interval. The area we do not include is what we call alpha. It's essentially the stuff that we just didn't think would happen. You know, there's like a very small, like I did this study, I gathered a bunch of, maybe asked 100 people if they had glasses or not. I created a confidence interval, but there is some chance that the true population mean lies outside of that interval. And that chance is alpha. Chance true mean is not in the interval.
Sorry, what is the word for
unincluded is the unincluded area where the chance true population mean is not in the interval. I would just bring this up and write it in the center, but I'm going to use that really soon anyway. That's what I want to keep both of these active when we're working on it. So hopefully, everyone can see this and read it. I purposely went to the supply closet and got nice blue bold markers for this.
They're brand new.
They're brand new. Yeah, I looted the supply closet just like an hour ago. So I hope you're enjoying it. Okay. So the numbers I'm going to give you, so actually let me start with this way. I think it's more fun if we derive it. Do we have space? Let's just erase this and let's put it here. Put that true right there. And then if you can't see this, Dennis, you let me know. Hopefully you can see this right here, this area. Okay, great. So we are going to have confidence level, and the alpha. And our standards are 95%, 99%, and 99.9%. And these alphas are 0.05, 0.01, 0.001. Now, I know what you're thinking. Why is this not 5%, 1%, and 0.1%? Honestly, I don't really know. For whatever reason, we like to have confidence levels as percents, and we then like to convert those percents into decimals when we talk alpha. Just deal with it. It might be because it makes things easier to put in, like, because we work a lot with the numbers, the actual numbers here in the equation, so putting them always in terms of 0.05 rather than 5%, maybe it just prevents error. You don't want to put 5 when you really want 0.05. Now, these numbers are reflected in what are called z-scores. If this is that interval like we have from the empirical rule, then the alpha is the area that is not included, which includes we use a blue, which is this and this, correct? We're good? Yeah. These together are alpha. If you take those two areas together, right, if this is 95%, then the red area is 5%. So that means that each one of these red areas is what value? What? 2.5. Exactly, 2.5%. It is always alpha divided by 2. So we are going to designate these values as z-scores subscript alpha divided by 2. Good? Yeah, this is, you can't see it right now, can you? No, okay, so that's what I was afraid of. Because I'm about to use this, so let's just, you all have this anyway. All right, I assume you have this. I just erased it. I assume you do. It's gone. No, what do you want? Okay, let's do it. Let's just rewrite the whole thing. %, 99%, 99.9%. Z alpha divided by 2. So what I want to do, you will never have to memorize the numbers I'm going to give you. You'll be on your exam and all that. But I think it's helpful to figure out where these numbers come from. To do that, we're going to switch over to Excel, and I'll show you on this area right here. Here is what we were working with before when we were deriving the empirical rule. And let's see if we can figure out, I want to try to figure out how far away from the mean I go, and then have an area right here that equals alpha divided by 2. That's what I'm trying to do. Everyone follow me? So, I can use norm standard invert to do this. And you note the only thing it's asking me for is probability, because it knows the standard deviation is 1, it knows the mean is 0. All we need to tell it is the area under the curve. And the area under the curve is what? I'm sorry, the area that we care about. This red part on the left. For 95% confidence. We know that alpha together is 5% or 0.05. But we only want, the way that this math works, it only looks at one side. So what do we do? Exactly. Or we can just put in the 0.05 divided by 2. Now, is this number going to be positive or negative? What do you mean? The number I'm just about to about to put in. It's going to be negative. Why? Exactly. I'm going to the left. Now, these critical values will always be positive, so there's two ways to fix this. One is to simply note that you're just going to take the absolute value, and it'll be 1.96. The other option is to take the other area, 1 minus that. and you'll get a positive 1.96. That's what I did. But it turns out 1.96 is our z-score. Do you remember when I was telling you, yeah, 2 standard deviations, that's 95% of observations? That was a lie. 2 is rounding. It's technically 1.96. It's not even technically 1.96, because as you can see, we didn't quite get exactly 1.96. But 1.96 is closer to the truth than 2. And we can see that here. I've set this up so that C1 just references D1 and then takes the negative. If I put in 1.96, I get exactly 95%. We good? All right, let's do the next one. Oops. So now I don't want 5% confidence. What do I want? What's my next one? 1%. Right? So let's just replace that 5 with a 1. You can take the absolute value if you want. That's the function ABS. So if you don't want to do it this way, if you want to do it like this, and then do ABS, and then do it like that, you can totally do that as well. That is the same thing. Oops. That is the same thing as doing 1 minus. Same thing as doing that. .576. And if we put 2.576 here, 99%. What do you think we put in for this one? This last one? So 0.0001, there we go. And we get 3.29. I'm just trying to make a mistake. 3.2. And these 3 numbers are numbers I am, again, not asking you to memorize. They're going to be on the exam and everything like that. But now you know how to figure it out yourself. And you can figure it out not just for these 3 predetermined ones, which are very popular. These are the standard ones. But you can figure it out for anything. You can then, but if you're curious, you want to know what the threshold is for 97.85, you can put it in 2. You just do 1 minus that, put it into the alpha, divide by 2, put it into the system, you get the same. Appreciate, too, how this makes sense, right? As alphas get smaller and smaller, the critical scores, these are called critical scores, they get larger and larger. They have to get larger and larger because we have to go farther and farther away from the mean. So this is Z alpha divided by 2. The Z is because these are Z-scores, and you saw that too when you were working with Excel, and you saw like it was, when you do the standard normal, it's asked for a Z-score, because Z-scores are always with the standard, it's a standard thing we use. The alpha divided by 2 is a reference that you are taking this alpha, and then you are splitting it between 2 tails. Later in the unit, we're going to talk about alpha just alpha divided by 1, or just alpha, Z sub alpha, where it's only 1 tail, and it has different Z-scores.
95% understand.
You mean the difference between these two?
No. Upper you got 95% when it's switched to make sure to confirm that it was correct. 1.96. So you have T1 true and then C1 true?
Mm-hmm. So this is just like we were doing before when we did the, I mean, I guess you didn't have that still on your screen, but yeah. So it's just like we were doing when we were doing the empirical rule, deriving the empirical rule. So we're doing norm S inverse instead of norm inverse, because I didn't want to type in 0 and 1. Right, remember, z-scores are always related to a standard normal distribution. Yeah, some things are just like, they're just there to make your life a little easier. I appreciate the .s extra thing that they added. Anything else? Okay. All right, so let's talk about the math. So far, I haven't actually given you the equation yet for confidence intervals. Here is the equation for confidence intervals. Again, you don't have to memorize it, but you do have to understand how it works. First thing we do is we take x bar. X bar is our what? Mean, right? Is our sample average, our sample mean. We are then going to do adding and subtracting. Now, in the notes, this is labeled as a minus above the plus, right? Because I couldn't find a plus above the minus, and it drives me crazy. I think this looks nicer, but this is a symbol that was available in Word. So they're the same thing. What does it mean? What? I'm sorry, what did you say, Audrey? Yeah, we're going to have two values, right? We're going to have, we're going to add, and then we're going to subtract. And so creating two values, thus creating an interval between them, right? Hence the name confidence interval. We're going to add and subtract to z alpha divided by 2. Do not consider this to be like two variables. This is one variable. This is one variable. I've seen people do this where they put the z-score in and then they want to multiply the whole thing by alpha divided by 2. So they'll put in like 1.96 and then they will like multiply 1.96 times 0.05 and then divide the whole thing by 2. Don't do that. Right? This whole thing is z alpha divided by 2. This is one variable. But there are two other variables to consider. So we're going to multiply by sigma and then divide by the square root of n. What is sigma? Standard deviation of the population. What is n? What was that, Bashava? Number of observations, also known as our sample size. Appreciate the intuition as to how this works. Why this makes sense. So naturally, as you increase z-score, as you decide to have a lower and lower alpha, you are then going to have a higher and higher z-score, which means your confidence interval is going to get wider and wider because you are trying to essentially say, no, I'm certain I know what's going on. I'm certain I know where like this thing might land. Right? I want to be more and more, I don't want to say more and more confident because it's not an emotional state, but I want to be sure, essentially. But as the data is more naturally diverse, that also is going to require you to have cast a wider and wider net and have a larger and larger area, have a larger and larger interval. So if we were doing hair length, what do you think has a higher standard deviation? The hair length of the population in general or the hair length of anyone in the military? Population in general has a higher what? Standard deviation. Why? Why do you say that? Because I think I have to get that's regulation cup, right? So we can assume that we can reasonably assume that the standard deviation is a lot lower. And naturally, if I want to get a true population mean of what the average military haircut is, or someone in the military what their average haircut is, I don't have to have such a large interval in order to capture that true population mean. I can, all the things being equal, have a pretty small interval, because as noted, as you know, Alexia, like naturally the dispersion is pretty low. So larger sigmas, larger random dispersion of what's going on in the population is naturally going to require a wider confidence interval. Does that make sense? Now, why do you think n, or the sample size, is in the denominator? Set aside the fact that we're taking the square root. That's, why we take the square root and not just divide by n is an artifact of the mathematics. We're not going to get into that. But I'm more interested in why n is in the denominator. Yeah, but you're just sort of right in the sense you're trying to put into context, right? So you reference the coefficient of variation. You're trying to put it into context. And that's what essentially we're doing here. Like if I only ask 4 people and I figure out 4 people's hair length, and then I ask like 400 people and I get their hair length, which one naturally do you think I should be able to have a narrower range as to what's going on? Which do you think, where do you think I have more information? 400, clearly I have 400. So naturally, if I want to say, oh, I think the hair length is between, 4 inches and 5 inches, that is going to be a lot more meaningful if I based it off 400 people versus just 4. As your information increases, which is reflective in your sample size, then the likelihood that you got weirder and weirder just by random chance decreases. And therefore, as n increases, this value decreases, and you can more reasonably establish a confidence interval. While you're looking forward to doing this math, you can be brutally honest with me. And okay, all right, so I'll give you good news, because this equation, at least part of it, is built into Excel. But we have a problem. When you look at Excel, and you use a function in Excel, what does it always output? What is always the result? Yeah, Julia? A single. Exactly. So Julia's getting right to the point, right? We have this problem. It always wants to output a single value for everything, because that means that value is confined to a cell. But as you know, Julia, we have a problem because a confidence interval is by definition 2 values. Right? It is a lower bound and an upper bound. It is a range. So Excel does not have the whole thing built into it. It only has, I'm going to do this in red, this part. This part is built in. And this part that I circled in red is called the margin of error. This is the margin of error. The margin of error is added to the X bar and subtracted from X bar, and that gives us our upper and our lower bound, and that gives us our confidence interval. As confidence intervals increase, z-scores fall, and we have to get a wider and wider confidence interval because the margin of error increases. As we have more dispersion within the data, all things being equal, we have to have a wider and wider confidence interval. As we get less information, as we get more information, then the margin of error, all things being equal, can decrease, and we can see more about what's going on, right? And as a result, we have a narrower confidence interval. Any questions on that? Nope. Okay, let's do it in Excel then.
I'm gonna open up. I'm gonna open up a new sheet.
So Theo works at Friendly Friends, a toy company. And every few years, the company makes slight alterations to its teddy bear. It's the best-selling product. While most changes increase sales, a few decrease sales, and the standard deviation of sales is always more or less the same at 15,386. The company just made changes to the new bear, so it's trying to figure out how many to produce, and we're going to create a confidence interval. So based on, so first of all, we have sigma, which we're going to set at 15,386. We also have an N of 341. And we have a X bar, our sample size, a sample mean of 143,512. You can put the commas in like I did here if you want. And then we have an alpha value. At 95% confidence, so at 95% confidence, what's the alpha value? At 95%, what's the alpha? 0.05. Are we good? Okay. Now, how do we do this? What's the secret to Excel? Equals, and then you do what? Type vaguely. I love it. Exactly how I say it. Yeah. Type vaguely what you want. What do we want? We want the margin. No, it doesn't. No, that's not it. We want what? Well, if we type margin of error, we don't get anything. I am argument returns the argument Q, an angle expressed in radians. I think we want that.
Wait, Z represents Z squared.
Yep. But we do want a confidence interval, so let's type, oh, there it is, that's better, confidence norm. We will talk about confidence T next class. But now note, it's not asking for Z. The equation asks for alpha. It will do the Z calculation itself. Yep, it will do the Z calculation itself. So that's what's cool about Excel is it will do a lot of these steps for you, but you have to understand what you're putting in. And when in doubt, you can always hit this FX button in the upper right-hand corner, the upper left-hand corner, I mean. Oh, and that will give you, that will open a little window and it will tell you a little bit more about what you're doing and what each of these things represents. So, confidence norm, our alpha is 0.05, our sigma is 15,386, and our N is 341. And we get that, 1633. Done, right? It's cool. Now, before we move on, let me show you exactly what it did. Because we can do more or less the same thing. We can follow our equation before and do, thank you very much, do 1.96 times sigma divided by, and there's a square root function of Excel, XQRT, N. This is what we just did. But you will notice we don't get exactly the same thing. Here's the $10 million question, why? Why do you think we didn't get exactly the same thing? Anyone? This is a hard question, I'll admit. Go back to sheet 2. This is what we calculated, right? Is that 1.96? No, what is that? Something oh so slightly lower. When it does this confidence norm thing, one of its steps is this equation. It like takes that 0.05 and then it divides it by 2, 1 minus that, and puts it in the norm S invert function, and then it uses it in the confidence. So we are using, when we put in 1.96, we were using a rounded value. Excel is too cool for rounded values. That's why we get a slightly different number. And if we take this function, copy, and then paste it in place of our 1.96, we get exactly the same thing. So again, you can see all the things Excel is doing for you. It can do all this really complicated things, but it's not going to output two numbers, not in a single cell. We got to do that part. So this is what we're going to call our margin of error, ME. So we have a margin of error, so what should we do? I'll give you a hint. The first thing we need to do is we need to find our upper bound, which we'll call UB. So what should we do? Excellent. So we're going to use equal x bar plus margin of error. And note I bolded it because that's nice to see, but it's really important part what we found. Yep. So here's our equation. And then, of course, we will do the opposite. So, exactly. Right. In other words, the plus and the minus. And you got a result of this. Did everyone get this result? About 415,000 and 411,000.
Could you show me how you got LB?
Yep. LB?
Yeah, LB.
Basically the same as UB. Remember, it's just add and subtract. For some, the way that Excel is built, it doesn't like outputting two numbers. As we will find out later when we do regressions and correlation coefficients and everything, there are things in Excel where it will output a bunch of stuff, multiple bits of information. That requires a separate thing in data analysis. But in simple functions that you put into Excel, it just, there might be some exceptions, but generally just like outputting one number, because then that number is assigned to a cell. So what do you think happens then if we increase our confidence level from 95% all the way up to 99.9%? Currently we have an ME of 163304. It's going to be a bigger range. How much bigger, Daniel? Did you say bigger range? I couldn't tell who said that. Okay. So why does it make sense? I'm more interested in why it makes sense that the range goes up. The margin of error went up. It was about 1,600. Now it's 2,700. Why does that make sense? So if we want to have a higher chance to capture that true population mean, then we have to establish a larger interval. The only other ways to do it is to change something else. We can't really change sigma, that's fixed. We can change n. If we're like, that's too big. That's like a range of that's a range of over 5,000. Could you narrow it anymore? How do we narrow it? Yeah, we would have to increase n, because you can't really decide to decrease sigma, because sigma is something that is the result of the population. So you can't really decide to decrease it. And if we were working with standard deviation too, that's the result of the sample. But you can go through the extra effort and maybe talk to 500 people. And the margin of error shrinks. Or 5,000. And it shrinks even more. Because now we have more information. Any questions?
What, by the way, is the distance between these two, between the upper and lower bound?
What is the range? I don't know that immediately it was a range of like 5,000 before. Now it's probably a range of, certainly more than 1,000. Not quite 1,500. I can do that math in my head. How did I do that? I could subtract the two. That's kind of annoying to subtract these two numbers though, right? Because you have to think about the 7 and the 2 and the 2 and the 4, and you can do that math, but it's an easier way, Michael.
2 times the margin of error.
2 times the margin of error. Right? How do you know?
I mean, it's based off of the mean, so you know one margin of error, this is the one margin of error, one way, one margin of error, the distance between them.
Exactly. Right? By definition. So if you want to know what the range is, just look at the margin of error and double it. It's about 1430. Looks like almost 1432. And indeed, the upper minus the lower, it's about 1432. Just a tiny bit shy. By definition. By definition. Any other questions? These z-scores we're using, these z alpha divided by 2, rest on a really important assumption. We assume we know sigma. We assume we know the population standard deviation. This is kind of weird, but first of all, recognize that that's why I mentioned in this example, oh, they make this fair many times, they make some small estimations, they calculate the standard deviation over many years. It's generally this standard deviation. So even if the actual average is the same, is changing year to year, the dispersion is pretty constant. Okay. That's critical because I have to assume I know sigma. If I know sigma, then I know the shape of the distribution. If you know sigma, you know the shape of the distribution. If you don't know sigma, then you have to rely on the sample standard deviation. And that is going to come with some complexities, which we're going to talk about next class. But appreciate how this is nice and clean. There is this weird thing though. How do you calculate sigma? That's right, don't all talk at once. You can calculate sigma with this. And I can never remember if the mu is first or xi is first, because like it doesn't matter, because then you always end up taking you always end up squaring it anyway. So, I know, right? 50% chance. So, this is how you calculate sigma. What variable is in sigma? You got a capital N. What else? Average. Average of the what? The population mean. What are we trying to estimate when we make a confidence interval? The population mean. So this is sort of weird. That's why z-scores are nice if you can get them, but you don't always know sigma. It seems like an inherent contradiction. How can you possibly be trying to estimate the population mean if you need sigma to estimate the, But it's because, again, sometimes there are cases when we have so much data, we know what sigma is, but maybe the dispersion is constant, but the average is not. So we have a pretty general regular dispersion, but maybe that center point shifts from one side to the other based on circumstances. So that's why I framed that friendly friends example in that way. But in everyday cases, you don't know sigma. And you have to rely on an estimate of sigma, S, the sample standard deviation. And because we know less about that, that comes with complexities, and that's why we have to use the T distribution. And that's why when we typed in confidence, you saw confidence norm and confidence T. And that's what we're going to be talking about next class.